Let's set up a randomized complete block design to run in R. I've already typed in all of the commands here, and I'll just walk through them with you. I want to make a couple of points before we get started, and this comes from the lecture in class. The first point is, again, that we really don't care about the blocks in terms of whether blocking is a significant effect or not. What we really care about is simply removing the variance associated with blocks, and in so doing, it makes the mean square error smaller, and in that way we have a more powerful test. So we don't care whether blocks are significant or not, we just want to remove that source of variation. So these data are for bacterial growth plates, and you can see the data in the table, the Excel table that's right below me. There's a control, and then treatment 1 and treatment 2, and then there are a series of 5 blocks, A through E, and then the NG plates. Those are the number of no-growth plates that came out of this incubator. So each block represents a different shelf in the incubator, and if you've ever done microbiology before, you, at least back in the day, when incubators weren't as good, I suppose, as they are today, the temperature wasn't absolutely consistent throughout the incubator, and shelves that were higher would likely be warmer than shelves that were lower. So we're trying to remove the effect of that in this design. Furthermore, these no-growth plates, these are actually transform data. So this is I believe it's the natural log of the number of no-growth plates that came out of this incubator. Notice when you look at this data, and these are on the web page as a CSV file, notice that block is not a numeric variable, it's a categorical variable. And if we don't do that, if we use a number there, then we're going to end up with a little bit of funkiness in our analysis of variance table. So because of the way R is doing the linear models, and it's not really making a distinction between ANOVA and regression analysis, we have to sort of force it to treat this as an ANOVA design. So if we would just treat all of these as a numeric variable, with blocks 1 through 5, what would end up happening is that we would end up with an incorrect number of degrees of freedom in the model. So by using a categorical variable, we solve that problem. Notice too that I've set these data up in a column form like this, which is not the preferred method. At some point I'll show you how to get it from the preferred layout, in the regular sort of tabular layout, into this layout within R, so that we can import the data in a more pleasing way and then manipulate the columns so that we get this particular sort of layout. But let's go ahead and look at the R code now. The first thing I do is RM, so I'm basically asking it to clear the memory. So there you see RM paren list equals ls close paren, and that clears the memory. I then create a new data set called RCB Data, and I'm using the read CSV command to get those data. And when I do this, file.choose open paren close paren, and header instead of header equals t, I'm doing a couple of things. By using the file.choose command, the computer R is going to open up a dialog box, and you can then use that to select the file that you want. And I obviously made a mistake here, typing in heater equals t instead of header equals t. Recall that the header command tells it that there is the first row within the Excel file is going to be the labels, or the column names, and you can see those here. So we have treatment, control, treat 1, treat 2, block, A, B, C, D, and E, and then NG plates for number of no-growth plates. All right, so we've chosen that. I then ask it, I put in the RCB Data command. Remember, I've assigned this file to a data set called RCB Data, RCB for Randomized Complete Block Data. And here by typing in RCB Data, I'm just simply asking R to print out the data for me so that I can inspect it and make sure that there are no errors. So we've done that here. I then attach that data set so that now we can work with it. I ask for a box plot, and I'm looking for NG plates with respect to treatment. I could also do the box plots with respect to block, but I don't care about blocks, right? I'm not even going to bother to look at them. I'm just doing that to remove variance. So I'm going to do this no growth plates with respect to treatment. And that provides this nice box plot that you see over here on the right hand side, and clearly there's some funkiness that's going on with regards to the distributions. They're not necessarily normally distributed. We're not going to concern ourselves with that too much at this point. If these were my data, if these were data coming out of my lab, I think I would try some additional data transformations to try them clean them up. So they're not strictly normal, but again, recall that analysis variance, especially these preliminary designs that we're working with, are reasonably robust with respect to moderate deviations from normality. So we're going to be okay. So now I'm creating a new sort of file here called rcb.mod. So a randomized complete block.mod, mod standing for model. And in that, I'm going to contain the results of this linear model, so LM for linear model. And then I specify what the model is. And this model will make sense when you go back and look at the model that we presented in lecture. Think about the yij equals mu plus alpha I and so on. So here I have NG plates, that's my y, is a function of treatment, right, plus block. So I'm actually looking at two things. Recall, we're doing a one-way analysis of variance, not a two-way analysis of variance. So I'm using the block here only to remove variance. I don't care whether block is significant or not. It makes absolutely no difference to me. So now I've done that analysis, and now I simply type in Anova rcb.mod. So this is going to return the contents, the Anova table, for what I've put in rcb.mod. And here we have the results. So we see degrees of freedom 2 for treatment. That's correct because we had 3 treatments. 4 associated with blocks. We had 5 blocks, so 5 minus 1 is 4. And then for error, we have 8 degrees of freedom there. Here are the sums of squares, the mean squares, and then the F values. And you'll notice over here that the F value associated with treatment is highly significant. Now, realistically, I'm not even going to look at the p-value associated with block because I don't care about it. The only time I'm going to care about what happens there is if, at this level right here, I'm not significant. Then I might consider some pooling, and that, of course, will depend on what's going on down here. That's something we cover in lecture. At any rate, one more point I want to make here. If you look at these numbers and compare them with the numbers that we put up on the board during lecture, you notice that there is a difference. There are some deviations, and that translates all the way over to the mean squares and the F values. They are subtly different. Why is that? The answer is round-off error. What you get in the numbers that I presented in class are numbers that were computed by hand. So I used calculator formulas and I used a handheld calculator. And the number of digits stored in a handheld calculator are fewer than the digits that are stored in your desktop computer. So what you're seeing in the results that I present on the board is round-off error, and the numbers that you see here are closer to the true values. Very good. I'll see you guys next time.